kind of introduction to this kind of new format. So this is the first lecture of our 2020-2021 season, and as I'm sure you've already gathered, it's via Zoom. So things are going to be a little different to our in-person lectures. So essentially, the only people who can actually talk are our presenter and me, but there's a Q&A kind of chat box. So if you go to the bottom, there should be, you should see a thing called Q&A, and you can write your questions in there, and then we can see them. And then so after the presentation, we can run through those questions and answer them. So I thought we'd do it that way. But obviously this is the first time we've done this, so bear with us a little bit. I'm sure as we go on and do more of these, we can refine a little bit. Perhaps we can, once we know someone's asked a question, we can actually unmute them and have them talk. But I thought today we'll keep it a little bit simpler. So moving into our lecture. So today's lecture is on the coupling dynamic performance of FLNG and LNG carriers. And our speaker is, and I apologize if I absolutely brutally mess up your name, he's GDO4 Collins Noafro, but we're all calling him Collins. Collins is a PhD researcher at Newcastle University in marine offshore and subsea technology. And in the group, and he's conducting research on the prediction of gap resonance for FLNG and LNGC side-by-side offloading operations, which involves all sorts of different simulations, which you'll be hearing more about tonight. He graduated in subsea engineering from Strathclyde, and as I said, is now at Newcastle University in the Hydrodynamics lab. And he also has some experience as an R&D engineer for Fengtai Engineering Company. So I think without further ado, we can start. If you'd like to share your screen with us, Collins.
Okay. Yes. Hello, everyone. My name is Collins Noafro, and I'll be going through the presentation for the numerical investigation on coupling dynamic performance of FLNG and the LNG carriers. Yeah, the content of the presentation is, first of all, we'll go through the backgrounds and the research aims. We'll run through the numerical analysis, and this we'll go through the frequency domain analysis. We'll do analysis for single body and multi-body, because we have two floating bodies on the free surface. And we'll get some results from there and go to the time domain analysis, where we'll extract our global performance for the FLNG and LNG hulls and also the connecting systems. We'll also run a model test to be able to get the damping for the gap resonance effects. For the introduction to the FLNG, what is FLNG? The FLNG stands for Floating Liquefied Natural Gas Facility. This combines the facility for liquefaction of natural gas, storage, offloading of the LNG to the LNG carrier. For industry practice, this the side-by-side offloading has been chosen for the use of the FLNG. These vessels are one of the largest floating facilities ever. From the pictures we see the picture of the Prelude, which is currently the largest floating vessel. It's approximately 500 meters long. And the main aim of this presentation is to illustrate the importance of the coupling effect and gap resonance problem for side-by-side offloading of the FLNG and LNGC. First of all, we need to understand what are the different methods of offloading and in the open ocean. We have the loading at the cam buoy, The CAM just simply stands for the catenary anchor leg mooring buoy. We have the tandem offloading and also the side-by-side offloading. From industry practice, the side-by-side offloading has been chosen for the FLNG due to the cryogenic nature which the LNG is stored, which is approximately minus 167 degrees Celsius. And for safety and the ease of and quickness of the offloading, the side-by-side offloading is preferable. And with this side-by-side offloading comes various hydrodynamic challenges. Due to the long, narrow gap when the two vessels are configured side by side, we have different hydrodynamic resonances. The resonances can come in form of a moon pool, which is the first picture. Also, we have a resonance from the side-by-side offloading configuration. This is gotten from the long, narrow gap, which is obtained when the two vessels are configured in very close proximity of distances of up to 4.5 meters. We also have another form of hydrodynamic resonance, which is internal compartment sloshing. But that is beyond the scope of this our presentation. And this internal compartment sloshing also has some significant effect on the hydrodynamics of the vessels. Now, gap resonance. What is gap resonance, and why is it important? Well, for the side-by-side offloading, this is done mostly in a benign sea. Mostly in the benign sea due to the very close proximity of the two vessels. And we know that everywhere in the ocean, we have long periods of swells from far away storms. And in practice, this low frequency, long period swells do not significantly drive a surface motion linearly of the two vessels. But however, it has been shown in literature and also in the, during model testing that a quadratic frequency doubling could take place, and this can couple with the gap resonance. And when this occurs, the wave amplitude or the wave height in the gap region is going to be significantly higher. It's going to be significantly higher than the wave height of the surrounding ocean. And this gap resonance coupling should when planning for the offshore operation. For our simulation, the gap resonance appear as standing waves. And our simulation will make use of potential theories. This physical resonance occur at certain frequencies. They cannot be removed, but for the simulation, we have to control it by adding a damping surface or the free surface. We'll start with the numerical analysis. For the numerical simulation, we'll be using DNVGL's SESAM, and the program runs with on a potential theory. First of all, we have to get our design concepts using Genie. From there, we move on to the Hydro-D, where we run the frequency domain analysis. And this runs on the mathematical engine of WADAM. And in the frequency domain, we run the single body analysis for the FLNG and the LNGC and make some comparisons. And then we run the multibody analysis in the frequency domain. And for the multi-body analysis, we have to impute a damping lead because potential theory often over predicts the wave amplitude in the gap region. So we have to impute a damping lead, but for us to get the correct damping factor, we need to run a model test to be able to get accurate damping factor for the damping lead. And then we move on to the time domain analysis. And the time domain analysis, we will input our connecting system. This contains the hovers, the fenders, and the mooring lines. For that fed down the mooring lines. Then we run the global motion of the FLNG and LNGCs, and also we see how these motions affect the connecting systems. For the connecting systems distribution, the FLNG and LNGCs for our model is made up of eight hovers, 4 fenders, and 15 mooring lines. This is just a planned view of the mooring system and of the connecting system. And it's we're using a turret mooring to enable the vessel's weather vane for different wave directions. So we'll just briefly run through some basic theory, which I believe most people will be familiar with. So the problem to be solved is we have our 2 vessels. We have our 2 vessels on the free surface, the small vessel representing the LNGC, the larger vessel representing our FLNG. Then we have our incident wave. For our investigation, we'll investigate the effect of different wave directions on the coupled dynamics of the 2 vessels. So because of the presence of this body on the free surface, the incident wave will be disturbed, and this disturbed wave is called diffracted waves. And also, when the incident wave impacts the body, the vessels move, and they also generate their own waves. This generated wave is called the radiation wave. This radiation wave creates damping effects for the system because the energy dissipates away from the body. For the potential theory, we assume that the fluid is inviscid. It has no viscosity. The equations we are going to be solving are conservation of mass. That's the field equation inside the fluid domain. Conservation of momentum. That's an equation of motion for the 2 bodies. And also the boundary conditions. So again, for the basic introduction to the theory, we have the general equation and some assumptions for potential theory. We assume that the fluid is incompressible. And also we assume that the flow is irrotational. And a combination of the two has to satisfy our Laplace equation. For the boundary problem, the boundary value problem, we have the seafloor conditions, which states that the normal velocity is 0 at the seafloor. For our program at infinity, there is no disturbance from the incoming waves. For the free surface boundary conditions, we have 2 conditions which we have to solve. First of all, we have the kinematic free surface condition, which states that water particle lying on the free surface will continue to remain on the free surface. And also have the dynamic free surface condition. This just simply states the atmospheric pressure outside the fluid is constant and set to 0. And finally, the last boundary condition is on the body, on the vessel. And here we set the normal velocity at the fluid to equals 0 on the body, or it moves with the motion of the body. For our concept modeling, we have the FLNG outline for the model which we will be investigating, and we have the outline for the LNGC. We have the data for the scantlings of our 2 models. The FLNG is 340 meters long, while the LNGC is 291 meters long. So for the center of gravity, we have to put, we come up with a simple mass model. This mass model is made up of different beams with different lengths and varying density. So the density is varied to locate the LCG, that's longitudinal center of gravity. And the mass model, the beams are located at varying heights for the center of gravity, the kg. And once this is set, we input these models into the Hydrodynamic. But for the meshing of FLNG and LNGC comes with a simple, there's a rule of thumb. So the minimum, we have to have a minimum of 8 panels for a wavelength to get some reliable results. For our meshing, we have the mesh density is 3 meters. The FLNG has a total mesh panel of 3,310 panels, while the LNGC has a total number of panels of 2,088 panels. It's also important to run sensitivity tests for the mesh to be able to balance out how refined you want the mesh to be, and also to reduce computational time. So for the frequency domain analysis, in Hydrodynamic, we have to input a free body surface, So this potential theory doesn't take into account the effect of viscous damping on the body. So therefore, it is important to include the critical damping metrics to play an important role for the resonance amplitude. For this, our first preliminary graph, which is where we put our critical damping matrix. We just have this for our role, and we see that if we put the critical damping matrix for the roll transfer function, it reduces the amplitude of the roll motion. For this second graph here, we make some comparisons with the motion of the FLNG and the LNGC. So we make some comparison between the RAO for the FLNG and LNGC. The vessel with the largest motion is found to be the LNGC, which is the the blue line for our heave motion and the sway motion, which I just presented here. The LNGC has low inertia compared to the heavier FLNG. And also the block coefficient of the LNGC is much lower than that of the FLNG, which also influences the higher motion of the LNG. So the resonance frequencies, and here we have comparisons for the drift motions for the FLNG and LNGC in the yaw drift motion and the sway drift motion. The resonance frequencies are different. So the FLNG is more into the low frequency region compared to the LNGC. So basically, for the single body, due to the geometric of the vessels and the center of gravity, the LNG, what we're expecting, which will have a greater motion compared to the FLNG. Still comparing the single body analysis, the FLNG has a much higher wave drift compared to the LNGC. The amplitude peak displays a phase shift. The FLNG has a higher amplitude drift, which shows the ability for the wave making, which is larger compared to the LNGC. Which simply means the geometry and the volume of the FLNG is larger, so it has much more ability to make waves or make radiation waves. For the single body analysis, we also have to run a QTF, or quadratic transfer functions, for difference and some frequencies. For difference and some frequencies. And here we have it uses Newton's approximation method to calculate the QTF. So when the two frequencies, omega 1 and omega 2, is very small, the amplitude of the transfer function is negligible. This is shown in the red arrow here. So if we can't really see it, but for the FLNG, the QTF, the maximum amplitude of the FLNG is higher than that of the LNGC because the mean drift force of the FLNG is greater than that of the LNGC. And therefore, due to this higher displacement, the FLNG second order frequency is more significant for the FLNG compared to the LNGC. Once we've done the comparisons, we move on to the multi-body analysis. We're still in the frequency domain. And with potential theory, it tends to overpredict the resonance response since the viscous damping is not included. So we have to add some damping using a damping lead. We also need to add to remove irregular frequencies inside the hull. We use Wadam or off-body points located in between the two vessels to act as a wave probe. These off-body points are used to measure the wave amplitudes in the gap region. So we have different damping factors. So since our investigation is focused on the effect of different wave directions on the vessels. We have the wave direction for the heading C, oblique C, and the beam C. We need to put once we put the damping lid, we need to get the different damping factors. But to be able to know which damping factor we need, we have to conduct a model test in the lab, which was conducted not long ago. So that's a brief summary of this picture. We have the two rectangular badges side by side. This is just representing the moon pool, which uses the same concepts. So the red is shows the panel to remove the irregular frequencies. The blue mesh is the damping lid, and the black mesh shows the hull of the vessels. For this our graph here, we see that when the damping lid is 0, the resonance frequency is extremely high, which is almost 7 meters. And the frequency has different modes, has the first mode and the second mode. So as we increase the damping factor, see that the amplitude of the wave elevation starts reducing accordingly. But we need to also carry out a model test to be able to know what damping factor would be suitable for our analysis. So we conducted a model test in the hydrodynamic lab at Newcastle University. We have our two vessels, the smaller vessel to represent the LNGC. We have the larger vessel to represent the FLNG. It's the dimensions of the tank. The wave maker hits it with the incidence wave. We use 5 wave probes, wave gauges, since we use WG. Wave gauge 1 measures the incidence wave. We have 3 wave gauges in the middle of the two vessels, and the last wave gauge to measure the diffracted waves. The wave gauge 3 is closer to the LNG. Wave gauge 4 is positioned at the center, and wave gauge 5 is positioned close to the LNGC to measure how the different locations of the wave probes will be affected by wave elevation. Since we're doing the effect of wave direction also, we position our two vessels for the beam C and for the oblique C. This is just the cases for the experiment. We have the vessels were put 2 different drafts. We have the beam C and the oblique C, and the 2 vessels were given 3 different gap distance. And we have regular waves, 10 regular waves used, and also irregular waves were also used. And we measured the different wave heights or different waves amplitude in the gap region. And we found out that at some certain wave frequencies, the wave height is extremely elevated. And that's where we get our different resonance modes. And with these 4 varying factors, we'll come up with simple algorithm to be able to predict when this gap resonance will occur based on our 4 different variables. So for the physical model, for our experiment, Our models were fixed because we were just focusing on the effects of waves on the wave amplitude in the gap region. So we have the fixed model for the beam C and the oblique C. Here we just have a picture of the regular waves from our 8 wave makers from the Newcastle Hydrodynamics lab. We also put a camera inside one of our models to further validate the wave probe. The internal cameras were used to measure the actual wave elevation in the 2 models. And here we see an internal view of the camera in one of the models. The red check is approximately 1 centimeter, 1 by 1 cm. This metal probe, this is the wave gauge, one of the wave gauge at the center. We use this checks to measure the wave height and validate it with the wave probe. So we just have a video of the regular waves, regular incidence wave for the beam C. We have a video of one of the resonance modes from our different frequencies. And from here, we see that the wave elevation or the wave amplitude is extremely elevated when the resonance frequency is reached. With this elevated wave resonance, this can cause some adverse effects for the motions of the 2 vessels, and the gap resonance should be taken into consideration. We have a comparison of our experimental model and the gap, the simulation in the frequency domain. Here we can see one of the modes. The dot represents the experiment. We can see the resonance frequency is approximately 0.9. So from there, we can now select which of the damping factors to use. Where is this? So once we finish with the frequency domain, we move to the time domain analysis. The time domain analysis, we use what we done in SIMA from DNVGL's SIMA. This uses the SIMA code and the reflex. The frequency, the hydrodynamic coefficients, which have been computed in the frequency domain, are utilized in the time domain. So we have the frequency dependent added mass, potential damping, and hydrostatic stiffness. So we extract this result from the hydro-D and then input it into the SIMA. And here we can also input our hydrodynamic coupling and mechanical coupling between the 2 vessels. This is also modeled in the time domain. For the coupling, for the mechanical coupling, this can be modeled by means of the coupling fenders, either a fixed or rolling fenders. And we also have the hovers, the springs or breast line. And in the time domain, we also model the mooring line. Just a brief summary of theories we used in the time domain. It's basically from the conservation of momentum, we used the equation of motion for the FLNG and LNGC based on Newton's second law. And here we have the added mass, which is gotten from the frequency domain. Also our damping, it's also gotten from the frequency domain. The metrics for the hull, and our external forces, which will act on the two vessels. Equation is basically for a single body. So the effects of the hydrodynamic interaction on the frequency dependent added mass and damping force incorporated in the coupled, our time domain, coupled added mass and coupled retardation function at infinite frequency. In this instance, our 6x6 matrix for the single body will now be written as a 12x12 matrix. Because of the coupling motion, we now have a 12 degrees of motion. So the I and J represents the I is for the FLNG and the J is for the LNGC. And it's easier to put it in a matrix form. So we have the 6x6 impulse function response function matrix. This is also written as a 12x12 matrix. For the coupled equation of motion for the two vessels, this is written as a 12 coupled equation because we now have 12 degrees of motion because the two vessels are now coupled. So our initial equation of motion will be written in this form. And the Fi is the force acting on the FLNG, and the Fj is the force acting on the LNGC. For the connecting system, modeling of our connecting system, we have the hover lines. This is defined as the hover lines are just basically thick cables which are used to moor our ships, used to moor the ship side by side, or it can be moored to the pier. So the hover lines are defined as force elongation coupling, and the purpose of the model is to describe the actual force, the shear force, just generally. For the fenders are equipments which are used to prevent the boats and ships from colliding against each other. We can have the roller fenders. The fenders are defined as compressive forces. The fenders are nonlinear, while the hovers are basically linear in nature. For modeling of the connecting system, we use turret mooring system, which consists of the turret assembly. The mooring lines have a catenary shape. We use a simple catenary mooring equations. This is made from a combination of chain, rope, and chain at the bottom. The mooring is modeled using simple catenary equation. We just have a schematic drawing of how the mooring lines are. We have 15 mooring lines, and we use a turret mooring system to enable the two vessels weather vane depending on the wave direction. Here we have 3 typical test cases which we will be running for this our presentation. We have the wind wave coming in the heading direction. We have the oblique C and the beam C, and we want to illustrate the effect of the wave direction on the coupled dynamics of these vessels and its effects on the mooring lines, the hovers, and the fenders. For the connecting system, as mentioned earlier, the mooring line set by an angle of 120 degrees. We have the four fenders and 8 hovers. This initial arrow represents the direction of the wind. This green line is represents the current. This is the wave in heading C. For this last one, we have illustrates the water depth. For our investigation, we use a water depth of 1,500 meters. It's just the simulation, the plan for our simulation model. It just shows the heading C, the oblique C, and the beam C. For the global motion of the FLNG and the LNGC, we have the preliminary results for our comparison for different wave direction. Here we have a summary of the motion statistics for the FLNG and the LNGC motion. The FLNG and LNGC, they experience longer period motion for the surge, sway, and yaw motions. The LNGC experiences for the heave, roll, and pitch motion. The LNG, which is red, experiences larger motion. The vessels for the surge, sway, and yaw, they move together to maintain the offloading distance. For the statistics, the peak to peak surge motion for the FLNG is 9.3 from the maximum peak to peak surge motion for the FLNG is 9.341 meters. And for the LNGC is 10.473, which shows that the LNG experiences higher motion for the beam C, for the heading C. For the sway motion, the peak motion for the FLNG and the LNGC observed to be 8.07 meters. And for the LNG is 8.088 meters, which is relatively the same for the sway motion. For the yaw motion, the peak-to-peak yaw response is 5.857 degrees and 5.896 degrees. For this our global motion, the peak-to-peak motion for the heave, roll, and pitch motions significantly smaller compared to that of the surge, sway, and yaw motions, which are the significant motions for further studies. So this preliminary result, we see that the surge, sway, and yaw motions are the significant motions, which needs to be analyzed further. For the effect of the wave direction on the vessel motion, we have a graphical comparison of the FLNG and the LNGC motion with we have the same loading condition, but different environment setup. that is different wave directions. And this shows the effects of the wave directions on the motion. The main surge motion is increased for the heading C. For the heading C, we see that the main surge motion is increased for the two vessels, while for the beam C, the sway motion is increased. This allows the vessel to weather vane around the turret. Okay. We also get some results for the tension loads on the mooring lines. Here we have a statistical processed table which provides a maximum, minimum, mean, and the standard deviation of the mooring line loads. For the heading C environment, on the port side, which is a mooring line 6 to 10, the port side, this experiences the largest loads for heading C, which is the blue is heading C, the orange is the oblique C, and the gray is the beam C. The largest mooring loads for this heading C, this statistical representation is for heading C. The largest mooring loads is 5,361.8 kilonewtons for the mooring line 7. And this utilizes just 29% of the braking loads, which means that the mooring lines are adequately designed for the duration of the side-by-side operation. Also, we have the fast Fourier transform loads on the connecting system has low frequency component. Thus, the low frequency surge, sway, and yaw motion of the vessel is critical for our mooring analysis. For the fender loads, the compression on the fenders, which this provide prevention against collisions of the vessels. When the vessels maintain initial gaps, the fender loads will be negligible. So we have, as the initial gap, we have 0 loads on the fenders. And as the operation progresses, the fender experiences a pulsating squashing compression loads. So the plots on the fender load show the collision is more at the, so we have our 4 fender loads, 1 and 2, which is at the forward of the vessel, 3 and 4, which are the aft. So it shows the fender loads at the forward experiences largest loads for the heading C and the oblique C. For the final connecting system, which is the hovers, tension loads acting on the hover lines. So the hovers are pre-tensioned at 450 kilonewtons. And this is measured to balance out the fender reaction forces. We have the 8 hovers. The aft hovers lines are the most affected from our analysis, which is the hovers 6, 7, and 8 for the heading C. For the beam C, the average out due to the weather vaning effects. The Hawsers at the stand experience the largest loads. So this is conclusion to just our preliminary investigation based on wave direction. in the side-by-side configuration, the FLNG have the uniform sway and yaw motion to maintain safe offloading arm distance. The hulls are located at the stern, sustain larger loads than those in the bow. The fender forces are in form of pulses, and the fender and the stern experience more collision than those at the bow. We have to introduce a damping lead in the confined region. The performance of the potential theory code can be significantly improved, and this was done through model testing was needed to accurately determine the best damping lead value for our investigation. This investigation was just a preliminary investigation which shows the effects of wave direction on the vessel. We also have to run investigation for the effect of gap distance and vessel draft, and make comparison with our model tests. Thank you.
Okay then, thank you, Collins, for the very interesting lecture. We have a few questions, so I'll read out the questions and then you can answer them. So the first question is, did you consider varying wave amplitude in the tests to understand the nonlinear effects?
No, I just varied the frequency, because we have 10 wave frequencies, but they have the constant amplitude. So we check the effects of the wave frequency on the amplitude in the gap region.
Okay, and following on from that, when implementing the time domain solution, how did you include the second order effects, QTFs, predicted in the frequency domain?
Can you repeat that?
When implementing the time domain solution, how did you include the second order effects, QTFs, predicted in the frequency domain?
So for the second order, and it's for the multibody, I would assume you're saying for the multibody. We just have to put the free surface. You put the free surface, then you put there's an option for second order free surface. Then you have to in multibody, there's an option where you can select because they had to update the softwares. Previously, the DNVG or the previous version, there wasn't an option for you to input the second order multibody analysis. But if you have the updated one that was released last year, there is an option for that in the multibody analysis. So you select it and you get your free surface mesh and run the analysis.
Okay then, we have two more questions which are basically linked. So I suppose the first part is, what is the real world application for this work, this research you've been doing? And then following on from that, have there been any real cases of damage or issues caused to ships by this coupling dynamic interaction? So we've seen the simulations and the model tests, but what's the real world kind of situation?
Well, basically the FLNG is a new technology because first FLNG, which is a prelude, I think it started operation last year. So they were still coming up with different data to be able to increase the safety for this side-by-side offloading. Like I said previously, it's usually done in a benign sea because of the very close proximity of the two vessels. And it has been shown in the literature and experiments that when you have long distance swells, when you have swells from long distance storms, this can couple with one of the modes in the gap resonance. And when this swells couple, we have what we call a quadratic frequency doubling. And if this occurs, then you have this resonance frequencies in the gap region, where the wave elevation is going to be extremely higher than that of the surrounding seas. And basically, we know the FLNG is supposed to be stationed there for a couple of years. And offloading takes place frequently. And if we have this resonance occurring, this can reduce the safety and affect the operations of the offloading arms. So it's just basically to increase the safety in the side-by-side offloading when this resonance occurs. What was the second question again?
Have there been any cases of damage or issues caused? I appreciate that FLNG is relatively new, but I imagine you'd have a similar thing happening when you have, for example, naval ships and they have replenishment at sea and they're side by side. So is there any examples of things going wrong in real life?
No, there hasn't been, there's no, in real life, there hasn't been any example, but it's been shown in experiments, in model tests, that it can go wrong. So it's best we prevent it from going wrong than waiting for, because the FLNG is a very expensive vessel, and we don't want a real life situation to happen before we know something can go wrong. So if we can prevent it, it's always better. And we can come up with algorithms to assist the dynamic positioning. So when we experiencing this gap resonance, the vessels can position themselves to reduce this wave elevation. So it's more of a prevention. And the vessels you were talking about, they're not as long as these FLNGs, which are minimum of 300 meters to 500 meters. So it's more of a safety concern and to prevent any collision that will affect offloading operation.
Okay then, thank you. There were no more questions than that. So thank you again. Normally in a live presentation, we would have a round of applause at this point, but so consider yourself to have received that. I have a couple of announcements for the Southern Joint Branch generally. So our next lecture is on the 10th of November, and it will be on second generation intact stability criteria, and it'll be given by Andy King from Lloyd's Register. And following on from that, we have a lecture in December, also on the 10th, mitigation of surf riding and broaching events for small pilot vessels. Now, it's our intention that both of those will also be Zoom lectures. So just keep an eye out. The advert should be going for the second generation intact stability criteria. I hope to get out next week. And so you'll receive an email from either Rena or IMRS, depending which one you're a member of. And again, that'll be through Eventbrite, and then that registers for you for the Zoom lecture. We do hope to improve, the slickness of the operation. I'm going to try and find some appropriate mood music for the start while you're all waiting for it to start. But thank you for bearing with us. And if you have any feedback, please email techsec, that's TECHSEC at southernjointbranch.co.uk, because I'd welcome any comments you might have on how we could improve this further, and try and get this working as best we can for the branch. Again, as I said, thank you, Collins, for your lecture, and say good night to everybody, and hope you have a good weekend.